I made a video today about the importance of the on resistance of semiconductors. Could be MOSFETs, could be a bipolar transistor, etc. etc. I only made not a very good calculation here in this part of the video, and especially there were some, say, minimal bad calculations, when of course we can talk about minimal bad calculations anyway. The whole idea about it all was that I wanted to show that in a semiconductor, could be a MOSFET, could be a bipolar transistor, anyway, there is a certain on resistance. So when such a semiconductor is set to its saturation, that means that it fully conducts here. There's always here between the two electrodes of the semiconductor, could be a MOSFET like this, or say NPN transistor or a PNP transistor, doesn't matter. And that's important, of course. There's always a voltage drop here in the range between, say, 0.1 or even 0.01 volt and approximately 0.8 volts. And 0.8 volt is directly related to the silicon transistor because of its physical and etc. properties. So with a silicon transistor, when it's driven into saturation, there's a 0.8 voltage drop. That means, say it's 1 volt, say 5 ampere flows here. That means that there is a dissipation of 1 volt multiplied by 5 ampere, that's 5 watt. That means that such a transistor, this one for instance, can get hot. And when we are talking about MOSFETs, their internal resistance when they are driven to saturation, so not pulsed, their internal resistance is very low, and that's important. When a semiconductor has a very low internal resistance, when it's driven into saturation, the heat dissipation will be much less. Of course, that heat dissipation depends on the supply voltage. For instance, when we have here 100 volts and an internal resistance of 0.01 ohms, say for a MOSFET, that means that there is more dissipation compared to the situation where this is 24 volts and at the same internal resistance. So here is kind of basic calculation. Ohm's Law here, and here the wattage, say the dissipation, that's voltage multiplied by the resistance. And there is an earlier video on my YouTube channel where I am talking about this issue, and then I'm only talking about a pure resistor, and in this case I also want to refer to a pure resistor anyway. Say there is a voltage drop in a semiconductor here of 0.8 volts and 10 ampere is flowing in that circuit. That means that the transistor could also be a MOSFET, dissipates 0.8 multiplied by 10 is 8 watt. And of course, when that internal resistance is lower, there's a lot smaller dissipation. So, referring to my earlier video, in fact it's completely the same that I published today. And well, there was the calculation here that I showed was not very precise anyway. Thanks for watching. Of course, well, when we are talking about semiconductors, could be that this is a NPN type. Could be a NPN type MOSFET or an NPN type transistor. In that case, here is the positive going to the collector in case of an NPN transistor, and the emitter goes via the load to the minus. And you can also connect the load in the collector lead, that's here. Now it's in the emitter lead. That differs a little bit in terms of how the circuit will work, but in general, about talking about say the current that will flow, it will not differ so much. And when we are talking about MOSFETs, for instance this one, the gate can be driven with a voltage and also with an N MOSFET. The positive here goes to the drain and the negative goes to the source, and you can mount the load in the source lead and also in the drain lead. I often have mounted in the past the load in the drain lead, and there are videos about this problem on my YouTube channel, and there are also comments where people say that you must mount the load in the source lead to prevent, say, dissipation inside the MOSFET. But anyway, I don't want to go in detail. Perhaps I will show the links to these videos when I can find them, because at the moment I have approximately 1200 videos on my YouTube channel. Anyway, it's all about the on resistance, and that's the crucial point in this video. And I think it was more or less explained. I'm not talking about a situation where a NPN transistor or a PNP transistor is driven by pulses. Only this is a situation where we have a kind of static charge, static current charge in cases of MOSFETs, and current in cases of bipolar transistors that will drive the transistor, MOSFET or whatever, into saturation. Pen over somewhat. Thanks for watching. Sorry for that earlier video, that was quite good. I surely know that, but the calculation was not very precise. It's all about the voltage drop that happens in a semiconductor. P-channel MOSFET, big bunch of MOSFETs, etc, etc. It's all, say, based on my experience with MOSFETs and bipolar power transistors.